Hello and welcome to a quick Matlab tutorial on my channel. I'm doing a Matlab series regarding thermodynamic simulations, as this is part of my work at the university, and this should be just a brief introduction into Matlab. So Matlab, there are tons of videos out there which describe how Matlab works exactly and what are the different functions. I want to get right into the details, so no long introductions. Basic concepts you must know if you're doing your Matlab work is how the Matlab program is built up. So you have your main command window in here where you can put your commands in. You have a workspace where your variables and also your matrices are stored, and also a command history where you see what you all typed in. Okay, that's basically all you have to know. Here is the folder you're currently working in, and now we are getting to the basic functions of Matlab. So Matlab, for example, understands basic mathematics operations. For example, if I do here a simple calculation, 2 plus 2 equals 4. So ans means this is stored in the variable ans, and I also can see that here in the workspace that I have a 1 by 1, I think it's a double type of variable, which is, yeah, 1 by 1 double, which is stored currently with a 4. Alright, now Matlab understands complicated statements or has some predefinitions. For example, pi equals pi, or sine of pi half equals 1. So those functions are already implemented, the basic functions. Okay, now we want to model a script, and for that reason I've prepared some productivity tools in here. What we want to do? We want to calculate the alpha, means the heat transfer coefficient in a one-phase flow. So basically you need material properties. What do you need for that? Maybe we start with the equations what we want to calculate. So what we know is that we can calculate alpha. Ignore that for a minute. We can calculate alpha. Let me set that in Greek letters. Alpha can be calculated by the Nusselt number. Nusselt number times the conductivity, which is usually described with a lambda. And this all divided by a characteristic length of the problem. So this is a basic formula where you can see also that the Nusselt number correlates the heat transfer with multiplied with a characteristic length with the conductivity. So if your building Nusselt number is equal to heat transfer multiplied with a characteristic length divided by the conductivity. So this is the basic equation. Now the problem lies in here. The Nusselt number can be calculated, and it depends on a variety of parameters. For example, it depends on the Reynolds number. It also depends on a so-called loss coefficient you have in there, and the characteristic length L, and another length of the profile. So you have a function which depends on different variables, and these variables depend on some variables itself. For example, the Reynolds number depends on the velocity and viscosity, and also the characteristic length in this case. So we will going this way, that we implement a different sets of blocks. So the first thing, if you want to do a program, if you want to script, make your mind up what you want to do. And for that reason, it's always helpful to do a mind map, for example. And in mind map we can look what we want to do. So target or aim is in this case the heat transfer coefficients. Therefore, it is needed that we know the Nusselt number. and the conductivity. But the conductivity is more related to material properties, but we have to guess that. Then for the Nusselt number, we need to know the Reynolds number, the Brundle number, and lots of different things. And then we need for the Reynolds number the velocity and the viscosity. And those are also material properties. Besides that, we have geometrical properties, like the characteristic length, the length of the profile, surfaces. Because in the end, we just don't stop at the heat transfer coefficient, but we want to calculate the heat transferred with a certain area. So we need some areas as well, but this I would rather put into a geometric property. Yeah, surfaces is the better word for it. Okay, now for the velocity, we start with a mass flow. So mass flow means some kilograms per second or something similar, and this should be transferred into a velocity. Therefore we need the density. So in order to do that, you have to put a second, or in this case a fourth step, with process quantities. And process quantities could be the mass flow. The mass flow is then transferred to a volumetric flow, which is then transferred to a velocity. Okay, so if you have a velocity here from the mass flow, you go in here, and with the velocity and the viscosity you get your Reynolds number. With Reynolds number and a set of other parameters you get a Nusselt number, and then the Nusselt number and the conductivity goes in here. You have the heat transfer coefficient. And then finally you have your aim, the heat transferred, which is depending on the surface and the heat transfer coefficient, as well as the temperature difference. So this is not a complete description of all one-phase flows. It's not a general, it's more specific for one case, one example, right? So this mind map could help you to understand the problem, sort case, but you have to, in order to script something, you have to put it into a PAP. And the PAP is done usually with Visio. And I prepared something for you. In this case, we will start with the program and put in some material properties. Then we have geometric properties, the process parameters. From the mass flow, we get to the Reynolds number with the velocity and the density, which we are putting in here. And then with the Reynolds number, we make a differentiation. Depending on the Reynolds number, different formulas for the Nusselt numbers are used. So in this case, if the Reynolds number is beyond 10,000, then it's fully turbulent, and then this formula will get used. Then the next case has to be if it's bigger than 2,300. Then it is in this transferring area between 2,300 and 10,000. Then you have a part turbulent. You have a turbulent flow, but it's not fully turbulent. Okay, a different number. And then you have the laminar if it's below 2,300, right? Alright, and then you get to your alpha, and if you have your alpha, you do your heat, and this equals alpha times the surface area times the temperature difference. So now let's start with the material properties. We will go back and forth. When we see that we need some quantity, we will define it in the material properties. But we will do that this way, that we will just start scripting and we will go from there. Alright, so to start a new script, you simply go in here and say File, New Script. And then you see something like that. I have different scripts open here. This is now my Untitled 3. And the most important thing for a scripting editor is what is the comment sign. The percentage sign is here, the comment sign. In this case, you have to put some infos in here.